All right, let us begin. There's something else to say. So as far as I can tell, the only one of your instructors that has posted a practice exam or study guide is Alameda. I hadn't seen anything on Lewis's Canvas or on Barn Canvas. Does that track? Okay. So what I did was I took the practice exam and the study guide from Alameda that he posted and posted it to our Canvas. So if you're looking for something, that's at least something to practice from. I'll point out the study guide he posted was basically just a lot of problems from the textbook. So I thought we might go over a few of those. I'm kind of looking at his actual practice exam, which has a question like this: find the formula for the sequence, and some questions about limits. I'll point out, I think this limit has a mistake because it says the limit is x approaches infinity of 3n squared plus n minus 1 or 1 minus 2n squared. Either that should be an n or those should be x's, but probably doesn't really matter. A couple more limits. And then another limit. A lot of limits on this practice exam. Another limit. A piecewise function that also asks you to find a limit. And I would, if it were me, I'd be asking a continuity question here as well, which I will do. And then some log, semi-log stuff. Seems like in my opinion, kind of a short practice exam, but it might be. I don't know. I feel like Alameda kind of has a reputation for giving relatively easy exams, so it might be an accurate reflection of what he's going to do. Okay, well, there you go. So yes, an accurate reflection of these kind of exams he gives. So I'm going to do a few problems in the same vein as all of those. And then once I've done that, which I don't think will take the whole time, we can kind of open it up to other things. So let's look at something like this. What if our sequence was given by the following? A sub 1, yeah, sure, like that. Seems fine. A sub 1 is equal to 1/2. A sub 2 is equal to negative 4/3. A sub 3 is equal to positive 9/4. Sorry, it's terrible. A sub 4 is equal to negative 16/5. And a sub 5 is equal to 25/6. Did you all have a question back there? It's a little loud. Thanks. So if we're looking at something like this, I see three things to look at. I see a numerator, I see a denominator, and I also see, when this is not always going to be true, an alternating sequence. So we have a positive term, and a negative term, and the positive term, and the negative. So I'm going to focus on those three things separately. So let's look at the denominator first. The denominator looks pretty straightforward. It's 2, 3, 4, 5, 6. So I'm thinking those are all increasing by 1. So it looks like my denominator, if I'm trying to find the formula for a sub n, well, 2 is 1 bigger than 1, and 3 is 1 bigger than 2, and 4 is 1 bigger than 3, and 5 is 1 bigger than 4. So it looks like my denominator is just n plus 1. I know it's a 1n because I'm increasing by 1 every time. Let's look at the numerator. Numerator is a little different. I see a 1, a 4, a 9, a 16, a 25. If you see this pattern, we should be thinking what kind of things? So one more time, I didn't quite hear you, sorry. They are positive, but they all look like what special kind of numbers? They're definitely all square numbers. So we're thinking something like n squared. And it's exactly n squared, right? 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 4 squared, 5 squared. And that's exactly, so a sub 1, the top is 1 squared. A sub n, the top is n squared. And then the last piece is alternating. Here's the easiest, fastest way to do the alternating. Start with a negative 1 to the n. Start with that, regardless of anything. If you know it's going plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus, minus, plus. Start with a negative 1 to the n. And then plug in your first n value. What's my first n value? 1. Plug in n equals 1. If I plug in 1, I get 1 over 1 plus 1, which is 1/2. But negative 1 to the first, is that positive or negative? It's negative. I don't want it to be negative. I want it to be positive. So if you get the wrong sign with what you've written, add 1 to your power there, and that'll fix it. Because now when you plug in 1, you get negative 1 to the second power, and negative 1 squared is positive 1. And that'll alternate every term the right way instead of the wrong way. So if I had just done that, it would have been negative, positive, negative, positive, negative. If I do that, it's going to be positive, negative, positive, negative, positive. That's the easiest way to deal with the alternating part. Just start off with -1 to the n, and if it's not right, make it -1 to the n plus 1. Or n minus 1 if you wanted to have some flavor, but really n plus 1 would be Questions about this one? Let's do one more. Let's say we have the following sequence, or terms of a sequence, I suppose. A sub 1 is 5. A sub 2 is 8 over 2, which I'm going to kindly not write as 4. A sub 3 is 11 over 4. A sub 4 is 14 over 8. And A sub 5 is 17 over 16. It would probably be beneficial if I rewrote 5 as what? Right. The rest of these are fractions. Might as well make them all fractions. So let's write 5 as 5 over 1. Okay, I want you all to figure out a pattern or a formula for the top part. So yeah, I'll give you a minute to figure out what's going on with the top. It looks like we're increasing by the same amount each time. To try to figure out the formula for the numerator of this sequence. Those of you on Zoom, let me give you the attendance form while I'm thinking about it. So if my numerator terms are increasing by how much each time? How much? Wait, the numerator, not the denominator, the numerator. We're increasing by 3 each time. So that means we need a 3 times n. Because if n is increasing by 1 every time, we need 3 times that to increase by 3 every time. So we definitely have a 3n on top. And now we're just going to adjust. If I plug in n equals 1, 3 times 1 is 3. But when I plug in n equals 1, I want to get 5. So I better add 2. And then I'm going to check the next one just to make sure. If I plug in n equals 2, 3 times 2 plus 2 is 6 plus 2, which is 8. You can even check one more. If I plug in 3, 3 times 3 is 9, 9 plus 2 is 11. So it seems like I made the right choice. For the denominator, my pattern is 1, 2, 4, 8, 16. I'm not increasing by the same amount each time, right? I'm increasing by 1, and then 2, and then 4, and then 8. But I am multiplying by the same number each time. Every time I go from one term to the next, I'm multiplying by 2. So I need something like 2 to the n. It's not quite right. So I plug in 1, I get 2 to the first, which is 2, and I want 1, which is 2 to the 0th. So what I really need here is not 2 to the n, 2 to the n minus 1. So that my power, when I plug in n equals 1, my power is 0. And 2 to the 0 is 1. And when I plug in n equal to 2, I get 2 to the 2 minus 1, which is 2 to the 1, which is 2, and so on, and so on, and so on. So that would be my formula for this. So, sequences. Good times. Let's talk about some limits. Sure, yes. So let me, I like this example, sure. So I can, these ones are fine, whatever. Let's look at the following example. So some limit examples. Let's do the limit as n approaches infinity of 1 plus 5n plus 6n squared over 8n minus 3n squared. I want you all to find this limit. Yeah, you all. I want all of you to define this limit showing all the work. So don't just say what the answer is. I know you might already know it, but actually show the work. And the work is dividing everything by what? N to the second. Divide everything by n squared. I do think you can skip this first step. You don't have to write it out like this. I like to write it out just to show the work, but I think it's totally fine to skip this first step and know that when you divide each term by n squared, things are going to simplify in the following way. You're going to get the limit as n goes to infinity of 1 over n squared plus 5 over n plus 6 over 8 over n minus 3. I'm just simplifying those terms. N over n squared reduces to 1 over n. N squared over n squared is 1. Same thing on the bottom. And then, as n gets really big, what happens to 1 over n squared? It's really small. So does anything else divided by n or n to a positive power. So all those things become closer and closer to 0, and we end up with 0 plus 6 over 0 minus 3, which is 6 divided by negative 3, which is negative 2. Which we knew was going to be the answer when we looked at the quotient of the leading coefficients. Yes, these are my leading coefficients here. I know I wrote it in kind of an untypical way. Untypical is not a word, atypical way. Not standard way. The standard way of writing this would have been 6n squared plus 5n plus 1 over negative 3n squared plus 8n. But we don't have to write it in the standard way, and it might not be written in the standard way. So your leading term is just the one that has the highest power in each specific top and the bottom. Let's look at another one. Sorry, I should. Okay, I'm going to stop. I'm going to try to stop asking if you have any questions. You should just ask questions if you have questions. I'm going to continue on unless there's any questions. So I had one all picked out here. Not you. Okay, let's look at this one. Yeah, sure. Let's say we want the limit as x approaches negative infinity of 1 plus e to the negative 2x over 2e to the negative 3x plus 5e to the negative 2x. That looks gross, James. Yeah, I like it though. This one I've written to be probably more challenging than it should be. Yeah. Do I really like the choice I made here? I really don't like the choice I made here, actually. Yeah, I don't. Oh, well. Yeah, we're going to change it just a tiny bit. We're going to make an easy change. Let's make all those minuses pluses. Easy to fix. Okay. So let me ask a question here. In the same sort of way that for the previous limit, we divided everything by n squared because n squared was the thing in the denominator that was growing the fastest, right? N squared gets bigger faster than n or anything else, really. Which thing would be getting the biggest, the fastest here? E to the 2x or e to the 3x? Right. It would be e to the 3x if x were going to positive infinity. But if you go the other direction, things switch. So if you're going to negative infinity, we're actually going to divide everything by e to the 2x because things are switched. It's kind of tricky, but it does work out that way. So we're going to divide everything by e to the 2x and see what happens. We have the limit as x goes to minus infinity. I'm going to show the work, but again, I think it's okay to skip this step and simplify. I'm dividing each thing by e to the 2x. And then I'm going to simplify. So I get 1 over e to the 2x. I'm just going to leave it as is. Plus 1. I might have led us all astray here, which I'm going to be really unhappy about for myself in a second here. Did I lead us all astray? I think I might have led us all astray, which is a real bummer. Yeah, but we can make it work. So here's what I don't like in problems like this. I don't like e to the negative infinity. It just always feels like it never wants to work for me. So what I should probably do here is, yep. Yeah, wow, I've really blown it here. I've really led you guys down the wrong path, and I am sorry. Yeah, is that the wrong path, James? So here's what I think is going to happen. And it's probably going to be wrong. And forgive me for being so wrong here. If the limit as x goes to negative infinity, this is going to be written as e to the negative 2x, and I promise you there's a reason, plus 1, over, 2 over e to the negative x plus 5. Okay, here's what's happening. Here's why I've written things this way. I prefer e to the positive infinity. It's easier for me to know that e to a big number is a big number. That's e to a big number, because negative 2 times negative infinity is a positive infinity. It's e to a positively big number. So this thing here is blowing up the positive infinity. I'm getting infinity plus 1 divided by, down here, this denominator is also getting infinitely large. It's e to the negative infinity, which is e to the positive infinity, which is e to a big number, which is a big number. But then it's 2 divided by a big number, so it's a small number. So on the bottom, we just have 0 plus 5. Infinity plus 1 is still infinity. Infinity divided by 5 is still infinity. Not my best work ever. Let's look at the other limit just for completeness' sake. What if we were going instead to positive infinity? The limit as x goes to positive infinity of 1 plus e to the 2x over 2 e to the 3x plus 5 e to the 2x. So now what am I going to divide everything by? Yeah, the thing I said before that I know it's been a minute. We're going to divide everything by e to the 3x, the thing that's getting bigger faster. I will say, even though this previous one kind of sucked, it was still the right way to do it. There wasn't a better way to approach that problem. So yeah. So here, we're going to divide everything by e to the 3x. Okay, I'm going to do it without showing my work. So I'm going to get 1 over e to the 3x. E to the 2x divided by e to the 3x is going to be e to the negative x, because 2x minus 3x is negative x. I'm going to get 2 on the bottom plus 5e to the negative x. And again, if you're me, or someone like me, you prefer to have e to a positive power. So I'm going to rewrite this as 1 over e to the 3x plus 1 over e to the positive x over 2 plus 5 over e to the positive x. And then each of these things that are 1 over e to a power, well, since that's going to be a positive infinity, you have 1 over something very large, which gets small. 1 over something very large, 5 over something very large. So we end up with 0 plus 0 over, very importantly, 2 plus 0. That 2 is important. If it wasn't there, we'd have a 0 over 0, which is a problem. But here we don't. We have a 0 over 2, and 0 divided by 2 is 0. Oh, limits. Really okay to ask questions if you have them. Otherwise, I'm just gonna keep on going. Yes. So yes, so I would say there is a general rule for ones where it's polynomials like that on top and bottom. So if you have, so for example, I'm just gonna give you 3 examples and tell you what's gonna happen. So if you have the limit as n goes to infinity of something like 2n cubed plus 5n plus 1 over 7n cubed plus 6n squared plus 3, since the top highest power and the bottom highest power are the same, or since the degrees are the same, the limit is equal to the fraction of the leading coefficients. On the other hand, if the numerator has a smaller degree than the denominator, so we had something like 2n cubed plus 5n plus 1 over 7n to the 4th plus 6n squared plus 3, then the limit's going to be 0, because the bottom is growing faster than the numerator. And again, you can see that really by dividing everything by n to the 4th. And then the top will end up being 0, and the bottom will end up being 7. And 0 divided by 7 is 0. Finally, and this is the one that's unfortunately is not super, the rule isn't always it's going to be this, because it depends on the signage. So if you have a higher power on top, like you had, say, 2n to the 4th plus 5n plus 1 over 7n cubed plus 6n squared plus 3, that limit's most of the time going to be infinity. But depending on the coefficients here, it could be negative infinity. So this is equal to infinity. If you have a positive here, it would be a negative infinity if the division ended up with a positive over a negative. So it kind of depends on the signage, but essentially the top is getting bigger faster than the bottom. So both the top and the bottom are getting positive, or if they're both the same sign, it's a positive infinity. If they're both if they're opposite signs, it's a negative infinity. But the general rule is that if the degree on top is larger than the degree on the bottom, your limit's going to be some sort of infinity. And those are the rules for rational functions like that. All right. More gross limits, because limits are gross. Well, let's look at this one. It's going to be very similar to the one that he chose for the practice exam, because I do think we should look at this one. So let's say we have the limit as x approaches 0. Sure. Let's say we have 3 minus the square root of x squared plus, how terrible do I want to make this? 5x plus 9 over x. And when you look at this, well, what should I do first? Sorry, can you hear you? That is the second thing I should do. What's the first thing I should do? Plug in 0. So we couldn't do that for the previous ones because they're going to infinity. You can't, I mean, I guess you can plug in, but not really. But when you have an actual number that x is approaching, you should always start by plugging that in. And if we plug that in, what are we going to get? I want you to be more explicit with your answer. Not just 0, right, which is not 0. So 0 over 0 is a very, very, very different thing than just 0. 0 is beautiful. We love 0. 0 is great. If my limit were, say, the limit as x approaches 5 of x squared, James, come on. Sure, x squared minus 5x over x squared plus 5x. We wouldn't do any silly factoring, even though we could, because before we did any factoring, we plug in 5. If you plug in 5, you get 25 minus 25 over 25 plus 25, which is equal to 0 divided by 50, and 0 divided by not 0 is 0. And 0 is a lovely, wonderful, beautiful answer. 0 divided by 0 is trash. Or what I should really say is 0 divided by 0 means there is more work to be done. Right? You cannot stop there, because 0 divided by 0 could literally be any value. That's why it's called an indeterminate form, because the value is not yet determined. We have to do the work to determine it. So now we're going to do step 2, which is multiply by the conjugates. The limit is x approaches 0 of 3 minus the square root of x squared plus 5x plus 9 over x times 3 plus the square root of x squared plus 5x plus 9 over the same deal. Oh, I know why that. Okay, sure, that'll be fine. 18 plus, sure. My answer is not going to be pretty, but that's fine. Not all your answers are going to be nice. Whenever you multiply by a conjugate, there are two things to remember, I think. The things that aren't conjugates, you just leave as is. So here at the bottom, which is x times something that's not its conjugate, we're just going to leave as x times that stuff. You don't want to multiply it through because we're probably trying to get that first x there to cancel out. And multiplying it through doesn't help us cancel it out. On the other hand, we definitely do want to multiply out the top. So 3 times 3 is 9. The middle terms cancel out. That's why we're multiplying by the conjugate, right? Your positive 3 times the square root and your 3 times this negative square root are going to add it to 0. And then you have the negative square root times the positive square root. So be careful here. You get the negative of the entirety of the argument of the radical. So it's minus x squared plus 5x plus 9. What should happen, if we've done this correctly, is that the things that need to cancel out in the numerator will cancel out so that whatever's left will have something we can factor out to cancel the thing we want to cancel out in the bottom. We should always be able to cancel out the thing that's making the denominator 0. That's always our kind of end goal with these limits. So here, the limit as x approaches 0 of, let's see, so you get 9. I don't really want to write the 9 because I know it's going to cancel. I'm going to get negative x squared minus 5x. And then the 9 minus 9 is 0. And then the bottom still, the horrible x times 3 plus the square root of x squared plus 5x plus 9. Factor out an x from the top. You're left with a negative x minus 5. Oops, I forgot something very important, which I might lose a point for. Gotta write the limit. If there's still x's in my expression, I have to write the limit as x approaches whatever it's approaching. The bottom is still x times all the stuff. 3 plus the square root of x squared plus 5x plus 9. Now we can cancel the x divided by x for a 1. And then we have the limit as x approaches 0 of negative x minus 5 over 3 plus the square root of x squared plus 5x plus 9. This is actually going to turn out not to be terrible. I was wrong. I mean, it's not the best thing ever, but it's fine. So plugging in 0 now. If we're plugging in 0, we no longer need to write the limit, and we should not write the limit. We're going to get negative 0 minus 5 over 3 plus the square root of 0 plus 0 plus 9. I don't think you really need to write all those zeros. Like you could have written just negative 5 over 3 plus the square root of 9, or even just simplified it as negative 5 over 6. That's our limit. So sometimes 0 over 0 equals negative 5, 6. Question? Yes, so we only use the conjugate. So typically I would say when you have a limit that's a 0 over 0 type, we usually do something. Sometimes that something is multiplied by the conjugate. And the times that it happens are exactly, yes, when you have a radical, typically. Other times you might get a common denominator because there's two fractions being added or subtracted. Other times we might just factor and cancel depending on what we're faced with. Yeah, question. What else is on here? Yeah, go ahead.
Helping with like the limit of x approaching infinity and then square root of 9x squared plus x minus 3x.
Sure. Yes, excellent question. Can you say it to me one more time?
All of that minus 3x.
Yeah, as expected. So I'll point out, this is another type of indeterminate form. So 0 over 0 is an indeterminate form. We've also seen the infinity divided by infinity, where we've had a lot of infinity divided by infinity. We just haven't really said it. Those are also indeterminate. This is another one. This is an infinity minus infinity. It could be anything. And very similar to the previous problem, we're going to multiply by the conjugate. So I would probably take the additional step of making this a fraction divided by 1, and then multiplying by the square root of 9x squared plus x plus 3x over the same thing. Yeah, this one's real fun. So let's do it. The limit x goes to infinity. Multiply. I want you all to multiply off the top. I'll write down the bottom. Everyone should multiply off the top right now. Yeah, see that problem right there. That's what you should get when you multiply off the top. The square root of 9x squared plus x times the square root of 9x squared plus x is 9x squared plus x. The middle terms cancel out, and minus 3x times positive 3x is minus 9x squared. Then we cancel the 9x squareds. Okay, here's the things that are a little bit tricky. You got x on top. You got the square root of 9x squared plus x plus 3x. And this kind of, although not exactly, but kind of looks like a rational function. It's not. The square root makes it not a rational function because the bottom is not a polynomial. But it kind of looks like a rational function where the highest power on top is 1, and the highest power on the bottom is also 1. I want to let that sink in for a second. Yes, I am correctly saying that this is similar to something where the highest power in the denominator is 1. Because you don't have x squared, you have the square root of x squared. And the square root of x squared is essentially, although not exactly, x to the first. So we are kind of thinking, oh, that looks like it's next to the first and the bottom. But how do we actually deal with it? This is where it gets to be tricky. So what we're going to do is the following. Now, yeah, we got it. So from the inside of the square root, we're going to factor out an x squared. So we're going to write this as the square root of x squared times 9 plus 1 over x. It's kind of like we're dividing each term by x squared. 9x squared divided by x squared is 9. X divided by x squared is 1 over x when we simplify it. And leave the 3x alone for a minute. I'm going to show an extra step here. I don't think we actually need to show this step, but I want to show it for you all. I'm going to rewrite this as the limit as x goes to infinity of x over. I'm going to break up the square root of x squared times 9 plus 1 over x as the square root of x squared times the square root of 9 plus 1 over x. It's a totally valid thing to do, right? It's kind of like saying, that's exactly like saying, right, the square root of 9 times 4 is equal to the square root of 9 times the square root of 4, which is 3 times 2, or it's the square root of 36, which is 6. Same thing either way. So it's perfectly fine to break up a square root of a product as the product of the square roots, as long as both things are positive. One of them's negative. It's a stupid thing. Okay, we're not dealing with that though. Okay, now here's the, so what I'm saying is you could have skipped this step though and gone straight to this step. And here's where this step is. I don't know what your professor thinks about you. I don't know what they want you to do here exactly. So I'm going to show you the exactly right way to do it, even though it's a little more work. So here's a question that has an annoying answer that's not what you want it to be. What's the square root of x squared? It's not what you want it to be. Not just x. It's not plus or minus x. The absolute value of x. Now, the reason I say that this is extra annoying here is because in this problem, is x positive or negative? Definitely, right? Where is x going to? As positive as it gets. So if x is already positive, then the absolute value of x is just x. What's the absolute value of 5? What's the absolute value of a million? Right? If x is already positive, the absolute value of whatever x is whatever x is. So here, since x is going to positive infinity, you just get to drop the absolute value sign. But there are other problems where that doesn't happen. So I feel like it's necessary to show that we understand that. Now, I don't personally think this is a very good test question. I know it wasn't on the practice, but like, I wouldn't ask this question kind of specifically to avoid that issue because it's just dangerous. Okay. Now we're in the situation where you can essentially divide everything by x to the highest power, which is x to the first. So now I'm going to write this as the limit as x goes to infinity of x over x square root of 9 plus 1 over x plus 3x over x. X over x is 1, x over x is 1, x over x is 1. So I end up with the limit as x goes to infinity of 1 over the square root of 9 plus 1 over x plus 3. The remaining 1 over x gets very, very, very small because x is getting really big. So you end up with 1 over 3 plus 3, which is 1 over 6. Kind of terrible. 1 second. I'm going to say one more thing. So I will point out, although I don't see this in the textbook at all, I would just mention that if this happened to be a limit as x was approaching negative infinity, if x was negative instead of positive, then from this step to this step, the absolute value of x would actually turn into negative x, not positive x. I don't think you're going to see that, but I would be remiss if I did not say it. Yeah.
Just to clarify, the x from 3x was removed because you factor out x, right? And then you can't.
The x from the 3x, like here. So I wouldn't say I factored out x, although there's a way to do it. I would say that I divided each thing by x. But yes, so I will point out, and actually I kind of had thought about going that way instead. You could have alternatively, sorry, I'm looking for a blank piece of paper here, apologies. So from this step here, if you prefer to not divide everything by x, but to factor out an x, which is also an option, right? When you're doing these ones with rational functions where you're dividing everything by the highest power of x in the denominator, you can alternatively factor out the highest power of x in the denominator. That's the same work really. So right here, I could have said that this was the limit as x goes to infinity of x over, and then from the bottom, from each of these two terms, I could factor out an x. And then be left with the square root of 9 plus 1 over x plus 3. And then those x's cancel. It's the same thing. Yep. So just to kind of go along with that thought for a second, if you prefer, if you're dealing with something like a limit as x goes to infinity of 5x to the 7th plus x cubed minus 1 over 6x to the 7th plus 8x to the 4th plus 9x, I can factor out an x to the 7th from the top and the bottom instead of dividing each thing by x to the 7th. And if I do it that way, I still get the same result. I get x to the 7th times 5 plus x to the negative 4th minus x to the negative 7th. I don't love writing it that way, but I'm writing it that way just to kind of point something out. On the bottom, x to the 7th times 6 plus, here I'm going to write it as 8 over x cubed plus 9 over x to the 6th. So it's like I've divided each thing by x to the 7th. X to the 3rd divided by x to the 7th is x to the 3 minus 7, which is x to the negative 4, which I probably would have preferred to write as 1 over x to the 4. Same deal here. I would have preferred to write this as 1 over x to the 7th. And then we can see, just like every other time, with x getting really big, all these things are going to get super small. So, and also x to the 7th divided by x to the 7th is 1. To end up with the limit, I should just not write that. I'm going to write the limit anyway. The limit as x goes to infinity. I know I said they're going to get super small, but I decided to write them again. Sorry, it's terrible, I know. But your answer is going to be 5/6, which we already knew because it was a limit to infinity where the degrees were the same on the top and the bottom, and the quotient of the leading coefficients was 5/6. So that's another, yes, you can factor out instead of dividing by it. It's really the same step. All right. Some one-sided limits. Okay. Like a lot of limits. I guess that means you know what you need to look at. Sure. All right, I see what we're doing here. Okay, let's look at that. Yeah, that's fine. Let's look at something like, but not, yeah. I feel like these questions aren't enough. So if I was asking a question like this, I would say, let's find the limit as x approaches 2 of x cubed plus, sure, I like a plus here, plus 3x over x squared. Sure. Sorry, I'm thinking about what I want this to be. 1 second. Apologies. Sure. Minus 5x plus 6. What do we do first? That's what we do second. What do we do first? Plug it in. So we plug it in, what do we get? 8 plus 6 over 4 minus 10 plus 6. We get 14 over 0. So unlike a 0 over 0, which is an indeterminate, a 14 over 0 is it does not exist, but it also usually means we should check out in what way it does not exist. So what it really means is you're either going to get infinity, negative infinity, or does not exist. And what that really means is we should look at both one-sided limits. So we're going to limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. And then, yes, we should factor it. So let's say I can factor the top as x times x squared plus 3, although it's not particularly vital to factor the top in a not 0 over 0 situation. You can, but it's really unnecessary. We do want to factor the bottom, which factors as x minus 3 times x minus 2. Nothing cancels, so I just start plugging things in. So I know the top's going to be what if I plug in 2? Well, when I did it before, what was it equal to? 14, right? 2 times 7, yeah, 14. Now here is where the magic happens. Plugging to the bottom, 2 minus 3 is -1. And a number a little bit smaller than 2 minus 2 is a little bit positive or a little bit negative. Imagine something smaller than 2 like 1.9. If you plug in 1.9, well, is 1.9 minus 2 a little bit positive or a little bit negative? A little bit negative. I like to write 0 with a minus sign as a superscript. I'm really just trying to figure out the overall positive or negativeness of this fraction. So I have a positive divided by a negative times a negative. So overall, the sign is positive. So this is positive infinity. Because when you divide by a really big number, the fraction gets super small. When you divide by a very small number, the fraction gets super big. Let's do the same thing down here. Same expression. But now when we plug in a number a little bit bigger than 2, the top is still 14 because we're actually plugging in 2. And the bottom is still -1 times a number that's very close to 0. But now this number that's very close to 0 is slightly positive. And now my overall fraction has a negative sign. So this is going to go to negative infinity. So the left-hand limit's positive infinity. The right-hand limit's negative infinity. And the overall limit doesn't exist because they're both going different directions. So the limit as x approaches 2 of x cubed plus 3x over x squared minus 5x plus 6. We can only say it does not exist. We cannot say it goes in one particular positive or negative direction. I just want to say there. I think it's good. Yeah. Questions about this? No? I think you do, yes. I don't know how else I would do it without showing this work is the real answer. Because if you plug in, so basically if you get a number over 0, I should say, if you get a non-zero number over 0, then you kind of have to figure out what kind of infinity it's going to. And that really means you have to look at the one-sided limits. So yeah, I think you do have to do this work here. Usually I would say most of the time if you're being asked a question like this, you're usually being asked to do just a one-sided limit, or maybe both. Like they're going to ask it as a one-sided limit typically. I just started off with the more general version of the question. But yeah, you like on the exam here, you're being asked to find the limit as x approaches something from the right-hand side. So typically for these ones, they try to make it so it's not so terrible. I mean, yeah. Okay, let's look at one more. I think I just want to grab this one here because I feel like, yeah. I don't know about this question here. Oh yeah, so I will point out, no, yeah, I won't point out. The thing I just said is exactly what I should have said. So here's the next problem, and I actually am using the problem from the practice test because I just want to point out how stupid it is, really. But also that we should look at. I don't really mean that, yeah. So here's our function. It's the square root of 1 minus x when x is less than or equal to 1. It's x squared minus 1 when x is between 1 and 2. It is equal to 2 if x is equal to 2. And it's equal to 2x minus 3 if x is bigger than 2. And for all this writing, I feel like, am I missing a page? No, I'm not. It doesn't even say find limit. It says consider the limit. Okay, I've considered it. Yeah, sometimes. Okay, so here's the terrible question that's being asked here. Find the limit as x approaches 2 from the left of f of x. In my opinion, you've wasted a whole lot of space writing all this to not ask more. So we're going to ask more. But first, let's find this limit. So if we approach 2 from the left, I want all of you to write down right here after the limit as x approaches 2 from the left, write down the piece of the function that we should be using. You have 3 choices, 4 choices really, I guess, technically. All right, drum roll. And the function is x squared minus 1. That's the piece we should be using if we're getting really, really, really close to 2 from the less than 2 side of 2, because that's where x is less than 2, but still really close to 2. We can't use this first piece, although x is less than 2 there. It's not close enough to 2 to use that piece to be the limit as x approaches 2. And we certainly can't use these 2 pieces because that's where x is bigger than or equal to 2. So that's the right piece. And then you would just plug in 2. And you get 2 squared minus 1, which is 3. And it seems like a whole lot of writing and space to not ask very much. So let's ask the better questions. If I were asking this, giving you this function, I would ask you, where is this function continuous? Because that's what's you use these type of functions for. So let's talk about continuity for a second. Specifically, let's talk about these 3 functions here. 2x minus 3, 2, and x squared minus 1 are all what types of functions? Start with a P. They're not parabolas. They're polynomials. Even 2, I know. Even f of x equals 2 is a polynomial. Yes, it's a horizontal line, but it's a 0-degree polynomial, which technically qualifies. All those polynomials are continuous everywhere. They're defined. On the other hand, the square root function is only continuous on its domain. So I'll point out that for the square root function, the insides, 1 minus x, better be bigger than or equal to 0. Or if I put x over here, I get 1 bigger than or equal to x. Or if you rewrite it, x less than or equal to 1. Oh, perfect. It works out. That's exactly where they've defined it. So that piece is also continuous on its domain. So the sum up here so far is that each of these pieces is continuous where they're defined. So all of this, I should say, this function is defined everywhere. Right? We're not missing any values. We've got everything from negative infinity to 1. We've got everything from 1 to 2. We've got 2, and we've got everything bigger than 2. So we're not missing any x values in our domain. So if they ask you about the domain here, I would just point out the domain is everything. There's nothing that needs to get excluded. Maybe we'll ask about the range too. Okay, so now we need to consider continuity. So there's only 2 places where we're actually worried about this function being continuous, where we switch from one piece to another. So I'm concerned about at x equals 1, because that's where we switch from this piece to that piece. I'm concerned at x equals 2, because that's where we switch from this piece to this piece to this piece. So we're going to look at both of those. So let's look at, since we've already looked at the limit as x approaches 2 from the left-hand side, let's start with x equal to 2 when we talk about continuity. So is this function continuous at x equal to 2? The answer is no. But we should show more work. So here's the work you should show. We're gonna check it. We're gonna check the three things until one of them doesn't check out. So there's three things to check. Does the function exist? Does the limit exist? And are they equal to each other? But as soon as one of those fails, you can stop and say not continuous. So let's look at part one. Does f of 2 exist? Well, yeah, f of 2 is equal to what? 2, right? They told us if you plug in 2, you get back 2. Okay. How about the limit? Well, we know the limit as x approaches 2 from the left of f of x was 3. And you could stop here, but I don't think you should. And here's why. I personally think it is a good idea to say why the function is not continuous. And at this point, we don't know if it's not continuous because the limit doesn't exist. We don't know yet. We haven't found the other side. Or because the limit exists and is not equal to the function value. One of those things is certainly going to happen, but I don't know which one it is until I do the right-hand side of the limit. So let's do the right-hand side of the limit as x approaches 2. The limit as x approaches 2 from the right-hand side of f of x is the limit as x approaches 2 from the right-hand side of, well, I'm going to use the right-hand side of 2, so I'm going to use the 2x minus 3. And 2x minus 3 is, if I plug in 2, I get 4 minus 3, which is 1. Those don't match, so here we get to say the limit doesn't exist. So no, it's not continuous at 2 because the limit as x approaches 2 of f of x doesn't exist. Let's look at the other side, or the other value where things might be weird. Is it continuous at x equal to 1? So we do the same thing. First we plug in 1. Okay, I'm plugging in 1 to the which piece? To the top piece, because that's where x is equal to 1. So f of 1 is the square root of 1 minus 1, which is 0. Now we're going to have the limit from either side of 1. The limit as x approaches 1 from the left of f of x, we're just using the same piece of the function. It's the limit as x approaches 1 from the left of the square root of 1 minus x. We would plug in 1 and we get the square root of 0, which is 0. Let's look at the other side of 1. The limit as x approaches 1 from the right of f of x. Well, then that's the limit as x approaches 1 from the right of, we're going to use this piece because that's where x is just to the right of 1. And if we plug in 1, we get 1 squared minus 1, which is also 0. So the limit exists and is equal to 0, and the function value is 0. And since they're the same, that means f of x is continuous at x equal to 1. So yeah, f of x is continuous at x equal to 1. And then if I were asking this question the way I would like to ask it, I would have asked it as, where is this function continuous? And then the answer we're really looking for is, where is it not continuous? So what's the only place where it isn't continuous? 2. So it's continuous everywhere else. So we would say, hey, this function f of x is continuous on the interval from negative infinity up to 2, excluding 2 itself, union 2 to infinity. That'd be a much better use of this piecewise function, in my opinion. Okay. I think he's got something wild on the back here. Sure. Okay. I don't love, I feel, so I like this question, but I don't love the fact that it's not, I don't, just like this question, I don't think it's asking enough, personally. I mean, surprise, surprise. So let's look at this monstrosity over here. So here's, oh yeah, can we even see all this? Yeah, gross. All right, so let's read this and see what we've got. Let's zoom in a bit. Okay, so here's the setup. Here we give an XY table from an Excel document along with a scatter plot, a semi-log plot, and a log-log plot for the data. So the first plot here is just the raw data, X versus Y. the second one here is the semi-log x versus, and I believe that should be log base 10 of y, not natural log of y. If someone accidentally writes natural log, you should just assume it's log base 10. And then thirdly, log, which is log of x versus log of y. Okay, great. Which plot gives the best approximation from the data and why? So we just look at them. Is it the first, second, or third? Which one's best fitting the scammer plot? The third one, clearly, right? It's hitting every point. But if it wasn't super clear, like maybe both of them look like they're hitting as many points as the other one, then you can zoom in and look at the R squared value that is given to you here. So if you look real closely here, here we have R squared equal to 0.9577. Here it's 0.9294, and here it's 0.9978. That's the one that's closest to 1, so that's the one you should pick. Okay. Zooming back out a tiny bit because that seems super close. So then we should read more. Which plot gives the best approximation? So the answer to that is the log. And what's our answer as to why? Say it louder. Yes, the highest R squared. Or I should say, really, I shouldn't say the word highest. Well, I mean, yeah, because it's the R squared that's closest to 1. Because R squared equals 0.99798 is the closest to 1. That's always how we know which one's the best fit. Okay, so I don't like this next question. Is the original data best modeled by a linear, exponential, or power function? Power. That doesn't seem like enough work. We should actually ask you to find the power function. Can we? Yes, we can, because we gave ourselves the linear equation here. So let's actually answer the better question, which is to find the power function. So find the power function. Sorry, let me zoom out a little bit more reasonably here. Sorry. So to find the power function, I'm going to take the linear relationship or equation that they gave me, which is y equal to 2.0032x plus minus, sorry, I'm smearing everything everywhere, minus 0.7079. Kind of gross, sorry about that. Okay, now I'm using a capital Y here and a capital X because I know it's log. Log, that means both y and x should be replaced with log of little y and log of little x. So your log or your semi-log tells you which things you get, right? If it's log, both of them are logs. If it's semi-log, which one is the logarithm? The y or the x? The y, right? Because it's x versus log of y. And the graph should tell you that, right? If you look at the semi-log one here, it is x versus log of y, if you can read that. I'm sorry. So then we're going to say that log of little y equals 2.0032 log of little x minus 0.7079. And then your job is to solve for y. And write it as, so our job really is to write it as y equal to some a times x to some power, right? We want to write it as a power function because we know it's supposed to be a power function. So first we do the thing we always do after you've written the log or semi-log linear equation is we write both sides as powers of 10. So 10 to the log of y equals 10 to the all this stuff. If it were me, I would have given you nicer numbers. Probably. 10 to the log of y is just y. We break this apart as two pieces. It's 10 to the 2.0032 log of x times 10 to the negative 0.7079. You have to simplify this further, in my opinion. You have to write this. You can do it in one step. I'm going to do it in two. This is 10 to the log of x to the 2.0032 power times 10 to the negative 0.7079. And then two more things, really one. I always like to write this first because that's like your constant. So I'm going to write 10 to the negative 0.7079 multiplied by the 10 to the log of x to a power is just x to that power. That's our answer. So that's what I think someone should ask, not just is it a power function, but what is the power function? Oh, I don't want it. All right. So as far as I can see, those are all the things on Alameda's practice test. Yeah. Definitely we do a half-life. Paper, any paper. So with these, with exponential growth and decay questions, really there's kind of two varieties of things that you can ask. I can either tell you, I can give you, so typically I have to give you 2 data points. And then I can either ask you, how long until we have this much stuff? Or how much stuff will I have after this long? So I can either give you a time and ask for an amount value, or give you an amount value and ask for a time. They're really the only flavors we've got. Sometimes it's more confusing because of how it's written, but really, if you break it down to like the base components, it's just, I give you a time, you tell me how much stuff, or I give you an amount of stuff, you tell me how much time. Okay, that said, let's try to make it confusing. So we observe that some quantity of an unknown radioactive material, I'm going to write it really terribly, decays by 17% over a 5-year period. What is the half-life? So reading this question, it might look like I haven't given you enough information, because it doesn't look like I've really given you any data points. But that's not true. We just have to be careful about how we read things. It's especially terrible that I haven't given you any amounts, but actually it's not. So if they don't give you any amounts, that's, in my opinion, kind of the best situation, because you can make up anything you want. So if I have to deal with percentages, what would be a really convenient amount of stuff to begin with? 100 grams, pounds, kilos, whatever. I usually use grams. But let's say our initial amount is 100 grams. So if I'm going to make up a little table over here, and I always recommend making up this table where you have your amount, or sorry, your time, and then the amount of stuff. I should also write down the model, right? You should all have memorized the model for exponential growth or decay. It's y of t equals c e to the k times t. That should be first thing you write down if you see exponential growth or exponential decay. So then I probably should have written decays exponentially to really drive that point home here, but that's what we mean. So here's what I've got. I know at the beginning of this process at time equals 0, I have how much percent? 100%, or 100 grams. Okay, now here's where I've written this kind of extra terrible to make it a little more confusing. How much time later? 5 years later. How many grams do I have? 100%. So I'm going to ask you all to read the question extremely carefully. And yes, this is unfortunately a way that people do write this sometimes, and it is annoying and hard to parse occasionally. So I'm going to read it out loud. The radioactive, so we have an unknown quantity of radioactive material that decays by 17%. So it doesn't decay to 17%, it decays by 17%, meaning we're losing 17%. And yes, I am sorry that people write it that way sometimes, but they do. So just be careful. If it says decays to an amount, that amount is what you have. If it says it decays by an amount, that amount is what you've lost, and you have to do 100% minus that amount. So we've decayed or lost 17%. How much remains? 100 minus 17, which is 83%, or 83 grams. So again, it requires very careful reading. You have to be careful when you read these exponential growth and decay problems. There's no getting around it. Again, I'm sorry. The English language is terrible. Okay, so the last question is, I should say, so you've got all the data we need to find C and K. So we're going to use these two data points to find our constant C and K. And then after we've done that, we're then going to ask the question, how long does it take until there's half of the stuff we started with left? So what time is it when there's 50 grams left? Because we want to do half of the original amount we started with. That's how we're going to find the half-life. All right, let's do it. So first things first. So I always feel like you can skip this first step, but you're going to plug in this first data point. So you're going to get 100 for Y and 0 for T. K times 0 is 0, e to the 0 is 1, C times 1 is C. So you end up just getting 100 equals C. And that's always going to be the case. If you know how much stuff there is at time equals 0, that is always going to be your C value. So then you rewrite your model. So now we update it and we say, okay, great. Now Y of T is equal to 100 e to the KT. That's our new, better model. And then we use this other data point. Okay, great. Well, now we're going to plug in 83 for Y and 5 for T. And then we're going to solve for K. So divide both sides by 100. 83 over 100, or 0.83. Notably, 83% as a decimal should always be what happens when you're using the percentage you have. That should come up on the left-hand side. Equals e to the 5k. Take the natural log of both sides. I prefer to write the natural log of 0.83 instead of 83 over 100, but it doesn't matter which way you do it. Equals the natural log of e to the 5k. But the natural log of e to the 5k is just 5k. And then divide both sides by 5. You get the natural log of 0.83 divided by 5 equal to k. So now our brand new finished model is y of t equals 100 e to that terrible number times t. So if someone asks you the annoying question, how much or what percent is left at time t, this is the answer as a function of t. That's sometimes it's more of like a web work thing. They say, tell me the mass of or the amount of radioactive material at time t. They're really just saying write the model with C and K solved for, but leave the variable t as the variable t. Okay, we found the model. Now we're going to solve the question that's being asked, meaning I want to know how long it takes to get to half of what I started with. I started with 100, so I want to know how long it takes to get to 50. So we're going to plug in 50 for y and solve for t. 50 equals 100 e to the natural log of 0.83 over 5 times t. And this process is very similar to what we just did solving for k. You divide both sides by the coefficient here. The 50 over 100 is a half. Not surprising that we get a half on the left side of this equation when we're finding the half-life. It would be surprising if we got anything else. So equals e to the natural log of 0.83 divided by 5 times t. We take the natural log of both sides, and I'm going to skip a little step here. I know that the natural log of, so on the left-hand side, I get the natural log of 1/2. On the right-hand side, the natural log of e to a bunch of stuff is just the bunch of stuff. So it's the natural log of 0.83 divided by 5 times t. I do not like dividing both sides by the natural log of 0.83 divided by 5. I don't like fractions and fractions. What I would recommend doing is multiplying both sides by 5 and then dividing both sides by the natural log of 0.83. It just looks nicer. And that is your half-life. Yeah. Up. Yes. Right. So we have 10 more minutes. Are there other questions or things I might not be thinking of that would be worthwhile? Yeah.
For trig, like limits approaching trig functions.
Sure. So Yes. I guess, do you have? I guess I'm not sure specifically, like, I have a couple ideas what that might mean. So someone could ask you like, what's the limit as x approaches pi over 3 of sine of x over 2? Oops, sorry, you can't see that, apologies. Really isn't a limit question. I mean, it is, but this is really a, well, okay, plug it in. I get sine of pi over 3 divided by 2, which is sine of pi over 6, which is 1/2. So that's more of a knowing how to evaluate a trig function question. Is that kind of what we're looking for, or something different?
I went more like,
Let me take one more crack at what I think you mean before you clarify. So we could ask something like the limit as x approaches 0 of sine of 7x divided by 3x. Is that more what you're looking for? Yeah, that's what I thought. So this kind of question relies on a fact that we talked about a little bit. We definitely talked about sine x over x, I think, at some point. So you have to remember that the limit as x approaches 0 of sine of x over x is equal to 1. Or more generally, the limit as some stuff approaches 0 of sine of some stuff over the exact same stuff, the stuff has to be the same, is 1. And here, the stuff isn't the same. Bummer. So what do? We make it the same. So here's how I would typically approach this. Limit as x approaches 0. I'm going to rewrite this as two fractions. I have sine of 7x in one of my numerators. I have 3x in the other denominator. And I'm going to ask the question, what do I wish was beneath sine of 7x? I wish 7x was there. That'd be great. But if you divide something by 7x and you don't want to change it, you also have to multiply it by 7x so that it's still the same. And then the x divided by x is just 1. So this x divided by x here, that's just equal to 1. Then we can rewrite this, and I don't think you actually need to write this up, but I'm going to write it out anyway, as the limit as x approaches 0 of sine of 7x over 7x times 7/3. And just to be completely explicit about this, whenever you have a limit of a function times a constant, you're allowed to pull that constant in front of the limit. So you could rewrite this as the 7/3 times the limit as x approaches 0 of sine of 7x over 7x. I think this is overkill as far as how much work I'm showing, but I just want you to see it all. So then, what does this limit have to be equal to? Right. So the whole thing is equal to 7/3 times 1, which is 7/3. For me, I probably at this point would have just said, like right here, it's equal to 1 times 7/3, which is 7/3. So that's how you do a problem like that. Let me show you, yeah, let's do one more. Let's do two more, actually. What about the limit? Yeah, that's exciting. As x approaches 0 of tangent squared of 5x over 3x squared. Well, that looks terrible. So here's the deal. You want sines and you want sine, right? Sine is the thing you want. If you plug in 0 here, you're going to get 0 over 0 because tangent of 0 is 0, just like sine of 0 is 0. So I'm going to rewrite this as in two steps. The first thing I'm going to do is I'm just going to break apart the tangent squared as tangent times tangent. So I have a tangent of 5x times a tangent of 5x times a 1 over 3x squared. And I guess I could write tangent of 5x over something, but I don't really want to right now. Because what I really want to do is then rewrite tangent as what divided by what? Tangent is a trig function divided by another trig function. It is, yeah, sine of 5x divided by cosine of 5x. And I still have my 1 over 3x squared. Okay, and now I'm gonna write it in this kind of wishful way that I like to write it, where my signs have blanks beneath them, because I find that to be easy, helpful. I don't know. I think it works. So I'm gonna rewrite this as limit as x approaches 0. I'm gonna have sine of 5x over blank times sine of 5x over blank times my blank over 3x squared. And then the cosines can hang out over here. They're not really that important. Cosine times cosine of 5x, or cosine squared of 5x. Because what's cosine of 0? It is 1. So that's not a problem, right? The cosine of 0 there isn't making us divide by 0. So it just kind of, you can push it off to the side. It's not really that important. Okay, just like before, what do I wish I had beneath sine of 5x? Everybody, what do I wish I had beneath sine of 5x? Right, I want the same thing that's inside the sine function. The argument of the sine function and the denominator need to be the same. And they have to be going to 0. Same deal here. But then if I put a 5x down there, I need a 5x up here and another 5x up here. And then I just put a 1 up here. Balanced, right? I divided by 5x twice and I multiplied by 5x twice. But now, each of these things in parentheses is going to have a limit that's equal to 1. And this thing over here, the x times x divided by x squared, those are going to cancel each other out. So we're left with something that has a limit of 1 and something that has a limit of 1 times 5 divided by 3 times 1 divided by cosine of 0 is 1. So we're left with 25 over 3. Okay, true or false? The limit as x approaches 0 of sine of x squared plus 1 over x squared plus 1 equals 1. False. Sine of, if I plug in 0, well, so what happens when you plug it in? What happens when you plug it in? I get sine of what? 1 divided by 1. And you know what sine of 1 isn't equal to? Not equal to 1. Sine of 1 is like, no, it's not equal to 0. Sine of 1 is something terrible. Like, let's see, 1 radian is close to 60 degrees. So sine of 1 is close to like 0.86. But definitely not 1. So the thing I want to emphasize about this example that was misleading you was I had sine of some stuff over the stuff, but the stuff wasn't approaching 0. All right, the stuff was getting closer and closer to 1. So this is a false. It's not equal to 1. On the other hand, this limit, the limit as x approaches 17 of sine of x squared minus 289 over x squared minus 289, is that equal to 1? I know it's kind of hard, but 17 squared is 289. So yeah, it's equal to 1 because you have sine of something that's going to 0 over the same exact thing that is also going to 0. So yes, this is equal to 1, the true statement. So sine of stuff over the same stuff, and the stuff, not what x is getting close to, but the stuff that you're taking sine of, if that stuff is getting closer and closer to 0, then that limit is equal to 1. All right, 3:30. I'll see you all on Tuesday. Good luck on all of your midterms.